Thank you, Gilles, for the fantastic introduction. Great, to the point. Yeah, well, no, welcome, Florent. Yeah. That's better. Okay, so yes, machine learning. I will talk about machine learning, and I will discuss slightly older stuff. No fancy diffusion and much simpler questions. Can neural network do anything, or something like this? Can they learn simple function? And so I'll try to review a bit some of the things that we physicists have been doing, and with a slight bias towards some of my work, unfortunately. But, so why is this? So if you started this business of machine learning 10 years or 15 years ago, it was basically solved. Okay, I mean nobody was interested in this, first of all. And you open a book like Understanding Machine Learning, and everything is clear. What you should do is optimize convex function, and we understand everything. It's all about bias variance trade-off, and you had a lot of theorems, VC dimension, that kind of thing. So everything was perfectly clear, and then neural net arrived and completely described these three pillars of wisdom. And it was a bit of a crisis, but of course everything works. Neural network works very well, so we have to understand. So no, we are not optimizing convex function. That's not exactly what we do these days. Neural networks are highly non-convex. They have really crazy functions. We had this bias variance trade-off that you should not use too many parameters. That's exactly the opposite of what everybody does. These things are massively over-parameterized, millions and now billions of parameters, and certainly they are not low-dimensional objects. It's really high-dimensional object, complicated geometry, which probably is good for us. And there is still no good theory about this, right? And that's one of the reasons we are here. So since we are, most of us are physicists, I think, we have this idea that maybe what we should do is starting with sample models. And for me, the essence, when we say physics of machine learning, it's not so much using Hamiltonians and Langevin dynamics, anything. Physics, for me, is really the fact that we like to think in terms of sample models and build from them, right? That's something that's the way we think. That's not at all what people were doing in statistical learning theory before, but we are thinking like this. The way we understand physics is basically by learning one harmonic oscillator does, then two harmonic oscillators, then you put many harmonic oscillators together, and we study this to death, right? We like sample models, and there's a joke about spherical cores in vacuum, and I'm preaching to the choir here, of course, but you have to. It's not a natural idea for many of these people to make models, but it is changing. Right? It's not just me being crazy. So this is from a slide from a YouTube talk from my friend and colleague Sebastian Bubeck, who is at Microsoft. And they say, oh, we have this new idea. We approach science of deep learning that roughly follow what physicists do, explore phenomena through control experiment, and build theories based on toy models, which that's revolutionary. Right? I think that's what Surya will call the scientific method, but. And so it's good, right? It means we can talk to those guys and try to look at sample models and try to defend understanding harmonic oscillators. So what will be my harmonic oscillators? Okay, so what I want to do, what I have been interested over the last few years, is trying to see if neural networks can learn very simple functions. Not that simple, but not very complicated. And so this class of functions are called the multi-index functions. Okay, what is it? Okay, so this is what it is. You have a vector who live in d dimensions, so it's just a d-dimensional vector. It's real and taken random, Gaussian. So you have taken a Gaussian vector. And what do? You project it with a matrix which is d times r into r direction. Okay, so you have your vector, you multiply by a matrix, and now you have R number. Okay, so multi-index means R larger than 1. And what do you do with this R number? You apply a function that turns these R numbers into 1. And that's your label. Okay, so that's a function that goes from a Gaussian vector to a real value. Okay, so let's look at example. So single index is when this matrix here is just one vector. So here you have only one number. So it's convenient to think about the projection of your data in this direction. So W star is one direction. So that's one function. Okay, it's a linear model. In statistics, you just return the projection of your data in one direction. Okay, or you can be more fancy. You can return the absolute value. That will be phase retrieval. I mean, phase retrieval will be if it will be complex. So this is the absolute value model if you want. Or you can take the sign, plus some noise if you want. That's what physicists like to call the perceptron model. Okay, so these are single index example, but you can be a little bit more fancy. You can project your vector into, let's say, 3 direction or 4. So now you have many of these vectors, or matrix if you want. And now G star, so just for notation, F star is applied to Z. But once I write the same function, but depends only on the projection, I call it G star. Okay, so G star now depend on R numbers. And, well, you can take H1 star plus absolute value of H2 star, or a polynomial. Think of any polynomial that you want. One of the things that physicists liked a lot, this is something called the committee machine. For each of these projections, you apply a nonlinearity and you sum them and you average. That's a small neural network. And from time to time, you might want to add some noise just for fun. Okay, so the rule of the game is now, I'm creating a data set with n such vector, and I compute the value, y. Okay, so this is sometimes called the target function, or in physics we usually call them the teacher function. And I'm giving you only this data set, so only z, only the vector and the result. So you don't know that, and you are trying to learn the function. Okay, so can you find this function? Okay, so that's a fairly simple question, and well, I think it's a good question to ask to neural network if they can do this, and how, and so on and so forth. Okay, so typically, what would we like to know? Well, how many data points would you need to have a fair approximation of the function? How does the error depends, if you are using different methods. So if you have a two-layer net, so it depends on the size of the net and the architecture, that kind of question. If you run a gradient descent or anything, how long should you run it? Can you make a classification of these functions? What are there hard ones, easy ones, medium ones, super easy ones, super hard ones, and so on and so forth. And ideally, if you talk to those guys, they are mathematicians most of the time. So if you give them theorem, it's great. But they are happy with physics, style. It depends who you talk to, but many of them are happy with physics style computations. As long as they understand them, which is not so easy. So we have to make an effort. And so that's what we are trying to do. In fact, as you will see, physicists have been doing that kind of stuff for a while. And now I have 4 parts in this talk. And part 1 is physicists already solved the problem, but they cheated. Okay, so let's go. What do I mean by this? So it's especially our community, we kind of looked at this in quite a long time. Okay, you can trace back some of these to the amazing work of Elizabeth Garner and Bernard Derrida. So that's 88, 89. There was amazing work done by some of the persons at this conference, including Mark. That's almost exact same questions was so well studied that there are already many good reviews from the 90s, which I strongly recommend. And then we worked hard, actually, with Jean Barbier, who is around here. At some point, we worked on making all these statements rigorous, and and Jean did amazing work on this. So all that we understood. So let me discuss a little bit what was done here and why it is a bit cheating. It's not cheating in the sense that they cheat, okay? They didn't cheat, but in the term of the question I'm asking today, using this result is a little bit like cheating, and this is what I mean. We are in a setting in which we assume to know G star, but we don't know W star. So this is cheating because I know already the form of the function. Okay, it's just the direction that I don't know. So this is cheating in the sense that I know that this is the sign of the sum of the thing or thing like this. So it's, it helps me a lot, right? So this problem is solved, and in that case, we just have to find the directions. Okay, so this is what I'm going to describe now, but you see what I mean when I'm saying it's cheating, because, in a machine learning situation, I'm giving you data, and you have to fit the data. You don't know what the function is. You don't even know it's a sign of something or the sum of something, and you don't know it's actually something that depends on these three directions and so on and so forth. So it's a little bit a cheat, all right? But if we don't know how to answer this, if we don't know how hard it is to identify these hidden directions, knowing they exist, well, it's going to be harder to do the rest. Okay, so let's try to see what happens. Okay, so the big thing that came out from what we did was when D is large in the thermodynamic limit, everything happens when n is proportional to D. Okay, in all those works, they are always when the number of data and the dimension are infinite, but they are proportional. Okay, and n over D is something we usually call alpha. Okay, and so I'm not going to review all this work, but essentially what's going on is something like this. If you look at the best estimate you can get from, let's call it W hat, if you look at the best estimate and you multiply it with the truth, W star, so my plots are usually one-dimensional, it's easier. You have something like this, when alpha, which is n over D, is small, or that's not the overlap, sorry, that would be 1 minus the overlap, because it starts at 1. So let's say the error on the overlap. Okay, at alpha small, it's large error, it's random guess, and when alpha is increasing, you go to 0, typically with something that goes like 1 over square root of alpha. Okay? So that's it. We need order D sample, and those guys are happy with order D. It's only us who are stupid enough to get precise. We work really hard to get precise statement, but order D is already good enough. So that's it. Well, not really, because this W hat is typically the average of W in a complicated statistical physics model, and you have to sample from it, and we know that sampling is hard. I mean, Marilou had an entire talk about it. So one thing you may want to ask is, okay, I know that in principle you need order D sample, but if we want to do it in practice with an algorithm that doesn't take billions of years to run, how hard is it to do that? So physicists also answered the question, and they answered it quite a long time ago. In fact, for all these problems, we know what the best efficient algorithm is. It's the TAP approach, the TAP equation. So who has never heard about Thouless-Anderson-Palmer equation? Okay, nobody. Well, why am I giving the talk? Maybe. So we have these equations, which are essentially some glorified Curie-Weiss equation. There is this Onsager term that helps a bit. So essentially, that was solved in 76. And even for those problems, it was, these equations were written a long time ago. There is this amazing paper by Mark, Garner Computation Without the Cavity Method, and he had a small paragraph called the TAP equation for this problem where he wrote them. But these are still the questions we use. Right? So Mark solved the problem in 89. And if you want to hear a bit about the history of TAP, I recommend this chapter 20 in the Spin-Glass Theory and Far Beyond book that I wrote with these people, where we review a bit the history. So this thing exists. I will not explain TAP too much. I just go, what they do. Essentially, that's the problem you have. You know that your y has been generated by a probability which is conditional to h, which is a projection. And h is your data time the direction that you don't know. Okay, so the way TAP works, essentially, is they say, okay, give me y, And I will try to get an estimate of what h can be. I'll try to have a guess. I will compute its means and the variance. Once I have h, now I will try, since I have z, to have a guess of wh given h. And once I do this, well, I will plug this estimate there and I will circle through it. Okay, and there is some Gaussian consistency, plus some hocus-pocus physics, on Zager term and so on and so forth. That's what the algorithm look like. Again, I don't want to go into detail. I mean, that looks a bit scary, but it's really not. It's really the tap equation, and if I would be working on SK, that would be really just Curie-Weiss and the Zager term. And there is a function here that looks really complicated, but if you look what it is, and it turns out to be a fundamental object, is if you give me y, what is the expectation of my guess on the field H, okay, on the projection. So that you can compute, because we are in the cheated scenario. We know what the probability is, so it's given by this integral, and this object is fundamental. So we can run this, and recently we wrote this paper where we did not do much. It's just redefining TAP for the multi-index model. And the good news is that we know everything. Okay? So when is TAP working? So first of all, that's not only this is a known question, but it's very easy to make a plot and tell you what's going on. So what you have to do is plot the free energy of your model in which you are trying to learn things, conditioned on the overlap. Okay? It's called the Parisi-France potential after this gentleman here. Maybe the France-Parisi potential. I'm sorry, Silvio. And if it looks like this, then it won't work, because what your algorithm tried to do is start from here and do a minimum of the local free energy. So you get stuck at zero overlap. Okay, but if it looks like this, anyway, zero overlap is the best thing. So there's not much. If it looks like this, your algorithm will work, because you will start here and you will go here and you will have a good estimate of the overlap. Okay? And you have the nasty situation, which is like this, when the best estimate is here, but somehow your algorithm fails because you get trapped here. Okay, so you should be familiar to this. It means trying to find direction in this model is literally the same as trying to find an order phase in a phase transition, right? So that will be like a liquid phase, if you want, where your order parameter is 0. That, let's say, the crystal phase, where the order parameter is positive, and this is what you get if you are in a supercooled liquid. You get stuck here while the truth is here. Right? So if I want to know if my algorithm works, I just have to essentially compute the derivative here, and that's all. Okay? If you want to do fancy math, you can also show that this is exactly the same as looking to the TAP free energy, which is a very complicated object, and you can look at the local Hessians of your free energy starting from the initial random guess. And what happens is that you can do random matrix theory, and this is something that we did notably with Antoine Maillard, who is here. At some point, if you have enough information, enough data, you have one eigenvalue that pops out, you have a negative direction, you follow it, and you find something. So all this can be done, and has been the subject of many studies. And at the end of the day, we can give a full classification of problems. Okay, so I'm going to give you the entire classification of which functions are hard. If you just want to guess, my definition will be, let's say I want a better than random guess on the hidden directions. All right, so first of all, let me also say that what we call TAP is often called in the computer science AMP for approximate message passing. And so sometimes I will use TAP, sometimes I will use AMP. So there are essentially three types of problems, three types of functions. There are the easy ones, the trivial ones. The trivial ones are the blue one here. They are functions for which the expectation of the field given h is different from 0. What do I mean? Well, I mean if you have something like this, and you know this is the form, well, it's kind of easy to guess what h is, right? There are maybe two solutions, but on average, y is giving you a good information on this. Okay? If for any value of, for all value of y, or sorry, for any value of y, there is an information, you can really invert it, that is trivial. and the slope of the potential will be negative. And for any order d amount of data, you will learn something. Right? If you start to think a little bit, this is really, really, really a mild condition. So you have to think really hard to find something for which this is not true. In fact, the only way this is not true is if you have a symmetric function. Okay? If you have y equal to the absolute value of something, well, if y is 7, then that guy is plus or minus 7. On average, it's 0. And for any value of y, this is true. So if I have an even function, unfortunately, the expectation of h given y is 0 for all y, so it's hard. So every time you have a symmetry, so for a single index model is just even symmetry. For multi-index model, that would be permutation symmetry. You can think of anything. Well, it's not so easy. And you need a certain amount of data. You have a phase transition. And if you have enough data, then finally you will have a transition. Right? So how much data? Well, that much. Okay? So it's a formula. You are supposed to take the expectation of h given y, square it, retract -1, take the squared, average it, take the inverse. Okay? And if someone has studied a special polynomial, you should recognize that this thing is the second Hermite polynomial. Okay, just a number, you can compute it. Okay, for the absolute value, it's 1/2. Okay, so these are easy functions, not so hard. You need a bit of data, and then your algorithm will work. And then you have the hard functions, and it's really hard to have a hard function. But essentially is, if you compute this, and this happens to be infinity, well, it means you cannot get the phase transition. You have to go to a number of data that scales larger than d. Okay? And it's really hard to come out with example. You have to really be creative. The only real example is this thing called parity. It's really a nasty example. So you give me r directions. You project in this r direction. You take the product, and then you take the sign. Okay? And in fact, it's known in the computer science that the parity problem is really, really, really hard. Okay, and we expect that for this problem, you need at least, the best algorithm we know needs something like d to the r minus 2. So it's easy if you have two directions, but then otherwise, it's, you need d squared, d cubed. It's really, really hard. So, okay, so that's the physics answer to the problem, and now we can knock on the door of our colleagues in computer science, and we say, okay, that's what we find. And if you do this, they say, well, that's really funny, because we work hard on the same problems, and they came out with something called the statistical query bounds, which I will not even explain. Okay, these are very, those guys are very creative. They are thinking, oh, any algorithm which is asking questions of the expectation of a function that is applied to the label and the data, given any algorithm that fit that class, we know that you have to have enough data to blah, 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 blah. And they have exactly the same classification. Okay? And they really believe that that class of algorithm, the statistical queries algorithm, capture a large, really a huge amount of algorithm. Not all of them. I mean, if we could prove that these are hard problems, that will be something like proving p is equal to np or something like that. So we can do this, but we are confident that there are probably no trivial algorithm that can beat this. Right? So that means we are good. Physicists did a good job. And we are really, really close to, we have the best algorithm, right? Good. So that's great. Yes?
So you were saying that the difference between trivial and easy is that at least you are assuming some non-injectivity. So when you have the even function.
With which one?
In the difference between trivial and easy.
3 and?
Trivial and easy.
Yes.
You were saying that you have non-injectivity and that was a problem in a sense. Right?
Yeah. But those can be also non-injective, right? I could have something like, for instance, if y is equal 7, I know that, it means h was 2 or 3, that's still okay. It's more than this. I need that it should be like, it's -1 or +1, so on average it's 0, and it should be true for all y. So you really need to have strong symmetries to have something like this. And it makes sense. I mean, it's a physics problem. We know there will be a phase transition only if you break a symmetry. So it's not very surprising for us, I think. Okay, just to show you example, this is the parity problem with two directions. So 2 is still doable. And you run the algorithm, and this is alpha equal n over d, and you have 0. Your guess is bad, then it gets good. We can do interesting function like this one. Okay, no, we can't. z1 squared plus sine of z1, z2, z3. So that's funny, because this is hard. But z1 squared is not. So what happens is that when I go close to 1/2, I learn the direction z1 squared, which means I know what z1 is. And this thing becomes a parity in 2 directions. And after a while, if I have enough data, suddenly, I learn the rest. So you have this this kind of funny moment where you're learning first a direction, it helps you to learn another direction. It's called the staircase. And that's the example that physicists came out years ago. It's called a specialization. If you have something like this, like a small neural network, at first, you are learning Z1, Z2, and Z3. They are learning something, but it's all the same. So you learn something in only one direction, and you need much more data in order to realize, I see, there were 3 neurons, and there are 3 directions. It's called the specialization. Yes, Alia?
In your previous slide, when you have first you learn Z1, and then you have a second threshold, is it the same one that you would have if you had just sine Z2, Z3, or is it larger?
It might, but it doesn't have to. They could also interact, and you have to look at the formula, and I don't want to do it now.
You don't know if it's higher or lower?
These are exactly the same for the previous one. All right, so that's it. Okay, so that problem is completely solved. We know everything. It's great. Tap MP is the best thing. Most problems can be solved with order D data. It's just this nasty parity, and all is fine. So the only problem is that we cheated. Okay, and it's bad because this algorithm knows too much. All right, so let's go to part 2. Okay, let's not cheat and use instead lazy machine learning methods, and they are not great. Spoiler. All right, so let's use a 2-layer net. Okay, so a 2-layer net will try to learn things by taking the vector, compute many projections, I call it P. P doesn't have to be equal to R. Typically, P will be much larger, but when people do machine learning, they take a large number of hidden units, and then you sum them up here. Okay, that's a 2-layer net. But I said we are going to use the lazy approach. So the lazy approach is where you actually don't even learn the first layer. I'm going to use random values here, and I'm not learning them. Okay, we start by this. So if you do this, it's actually very easy to realize what is going on. I mean, if you plug me Z, you give me a point, what this algorithm is doing is taking a bunch of, think of sigma as being a cosine. It will be a bunch of random Fourier modes. And then what I'm doing is learning the A. So it's really like I'm taking P Fourier modes, and I'm trying to fit the function with some Fourier modes. And of course, if I have enough of them, I'm going to succeed. Okay, so you can think of this. It's called the random feature model, but if sigma is a cosine, it's really a random Fourier model. And it's really easy because you don't have to do much. You can forget that this thing exists because you can compute the value of the vector here for any value of the vector there. So it's really about fitting those guys. And that you can do by least squared. Okay, it's a convex problem. Okay? The problem in machine learning is learning the W's, but I'm not doing this. I'm learning only the last layer. Okay? So this is very easy. Okay, so now I'm trying to approximate the true function by some random Fourier modes. All right, so why do I do this? It turns out that it is actually something that people do. The people who invented this, it's called random features, got an award, and then they got a taste of time award. So if it is good for them, it's good for us. It is also interesting in the sense that if P is going to infinity, this thing is really blowing up. You can show that this is equivalent to what is called kernel methods. It's also equivalent to Gaussian processes, and these are things that people love. So it makes sense to wonder if this thing works here. And then recently, 5 years ago, there was a lot of work and excitement about something called lazy training, where people show that even if you take a multi-layer neural net and you learn all layers, if your neural net is just comically oversized, it's really huge, super huge, and you train it in a weird way, you can show mathematically that if this thing is that big, this is literally the same as doing that. Okay, this thing is really equivalent to this mathematically. That's called the neural tangent kernel. That was proposed by some of my colleagues in EPFL and then expanded by people at Google and in Paris. And when it came out, people say, "Oh, that's it. Neural network is solved. They are just kernel methods." Okay, of course, from day one, I was saying that they are idiots. But I mean, I think it's a great work, but the idea that explains machine learning is really, really naive. Okay, and in fact, we are going to see this. But it was one of the first work when we could understand something on machine learning, so that's why it generates excitement. Okay, so great. Does it work? And unfortunately, for this problem that we are doing now, this is very limited. It turns out these techniques are really not so great. So what are they doing? So we worked a lot on this, a lot of work on these random projections, including by many people, including people in my group, and there was a fantastic work by Silvio recently. And in a nutshell, these things are just doing polynomial approximation. So it's really terrible. So if you take n and p, which are scaling like d to the kappa, what happens is that if they scale like d, you can only learn a linear part here, which is not a good way to approximate function. Okay, so let's take d squared data and something even bigger, p equal d squared hidden layer. Well, great. Now what you are doing is doing a quadratic approximation. Okay, let's take d cubed, which is like infinitely more data that we had in the cheated version. And now, well, yeah, we learn the cubic term. I mean, you might have as well done some polynomial fitting directly. Okay, so it's really not so great. And okay, well, that's what it is. So we can study why is it so. I have a small computation to show it, but I will skip it in the interest of time. But essentially, what you can show is that after the first layer, your data behave essentially as a linear projection of the original data. So you are trying to, it's worse than this, by the way. They not only look like linear projection of the data, plus noise. So it's even worse. Right? So in this regime, what happened is that you think you are doing something clever, but you basically are doing a linear model. Okay, this is when n and p is order d. That's something that was started by Sebastian Gold, who is also here. So everybody is here. I should be careful to what I say. Okay, so what should we do? Well, clearly this is telling us that we cannot use random projections. We cannot use a fixed random layer. We need to have the layer who knows something. Right? So before trying to see how we can have the first layer learning something, let's see how this will change if we, I'm cheating a bit, I will say, let's say that the first layer is still random, plus a rank 1 matrix where U is random, and I'm giving you W star. Okay, I'm just giving you a random spike in the right direction. All right, so let's assume that somehow, instead of a random projection, it's random plus a little bit of a perturbation in the right direction. Well, it turns out that this is changing everything drastically. Now, if you do this, and this is slightly for expert, instead of having this Gaussian equivalence, which is linear, which is okay, what you see at the second layer is just a matrix given your data plus some noise, you are seeing something that looks like this. Right? So bear with me now. If you decompose your data into the one that goes in the right direction of the teacher, plus sorting orthogonal, okay, so this one is a learned one, what happens is that you have now something that looks linear, but it's linear in the orthogonal direction, and all these coefficients in front, except the noise, they are non-linear in terms of the projection. So just by this, once you look at this fixed neural net, just having one spike in the right direction, suddenly your equivalent map is becoming non-linear in all directions that are in the direction of the thing that you have learned. So you can work a little bit on this if you want. We have a paper with Hugo Cui, which is very recent, where we solve this with replica and random matrix theory. Okay, I will not bore you with detail, but you can compute exactly what is happening in this direction, and essentially, you have enough data to learn everything. So if your W is acquiring information, it doesn't have to be perfect, right? But if the W is acquiring information over W star, suddenly, with N and P order D, we are good, right? We can fit very, very well this direction. And so, there is this dichotomy, which is very interesting. If you learn some direction, if you W's learn some direction, you can fit almost perfectly the teacher in this direction with N in order D. Everything which is in the complement space, so let's say at two directions you learn only one, well, everything in the complement, you cannot beat random features, so you are doing a polynomial approximation. That's not very surprising, I think. But that's telling us something. We need to learn the directions, right? So feature learning is needed. We need to have an algorithm where your two-layer net, your W's here, needs to do something and try to learn some of these directions. This is the only way we can beat these nasty limitations. Okay, so how are we going to do this? Well, that's kind of a rhetoric question, because obviously that's what everybody does. We are just going to run gradient descent, right? But gradient descent not only on the second layer, but also on the first layer. Okay, so life's too short. I'm not going to worry about the second layer from now on, just about the first one. And let's say if I run gradient descent on that many data or that many long, is it true that my W learns the W star? Yes? So that's a good question. Essentially, okay, I don't know the exact rate, but once you know the direction, the error is, okay, basically the error is decaying like something like this. 1 over P. P is the size of the layer. So if you want something which is good up to, 1 over 10,000, let's take P equal 10,000. But it doesn't have to grow with D. That's the beauty of it. I don't need to be that much. But it makes sense, because before I was trying to approximate something which was high-dimensional. Now I basically have one projection in one dimension. So it's, you are basically asking me how many Fourier coefficients do I need to approximate a function? Well, you need a bit, and you can work, but usually you don't need billions of them. Okay, so let's see what happens. Pier Francesco already talked about this. And there are billions of work on this. So let's first discuss what happens if you do fresh batch of data every time. So that means you are giving me one data point, I'm doing gradient descent, and I throw away my data. You are giving me one data point, I do gradient descent, I throw away my data, and so on and so forth. I never see any data twice. Okay? Why am I doing this? Because it's easy. So I will do this. Well, the truth is, that was also discussed by physicists, especially by David Saad and Sarah Sola in 1995. And then it was kind of rediscovered recently. But the bottom of the idea is that you can write the time evolution of the overlap, and the important one is M, which is the overlap between your W's, the one you are trying, the one you are, of your network, and the W star. And we can write an ODE on this. So again, tons of work. They do this. Then with Sebastian, we kind of try to prove it. Then we did it again with stronger guarantees. If you do that a long time, actually, you don't have ODEs, you have SDEs, because you have fluctuations. That was discussed by Gérard Benarous. If you do this and you have P going to infinity, then you can write a PDs on the distributions. That's something that connects to tons of work that were done in math. And okay, let me skip this. The whole point is that we have been working on this a lot. Okay, so let me tell you what is going on and skip all the difficulties. And I'm trying to give you a heuristic derivation of what is going on, in which we have only one direction and one neuron. Okay, because otherwise I cannot do it on the fly. Okay, so essentially, when you do gradient descent, this is what happens. Okay, let's do spherical gradient descent. So W is constant to be on the sphere. What you do is W is W at the previous time minus the learning rate times the gradient. And then you have to normalize to make sure that you stay on the sphere. Okay, if you realize that, this is 1 and gamma is small, this is close to 1, you can expand. This is how it looks. Okay, and what I'm really interested in the projection of my vector to the truth. Let's call it M. Okay, and so we have M of time t plus 1 is M of t minus gamma, the gradient, the projection of the gradient to the true direction, minus this term, which stays here. Well, if you have something like this, obviously what you do is you take this M of t, pass it here. This gamma, you pass it there. Gamma is going to 0. This is becoming the derivative. And since you average many, many data, it makes sense to say that, well, here it's basically the average of this projection. And you can write this ODE. Okay? And there is really not much more than that. That's the way it works. Okay, so let's look at this ODE, because this is where you can understand everything. So the derivative of your overlap, and what we want to know is when the overlap is growing away from 0, right? Is given by the expectation over data of the truth, so the projection of the data towards the true direction, and we apply the function, times the gradient, which is given by this. Okay, that looks a little bit, not trivial, but it is trivial, because of course you remember that my data is Gaussian, so these are just two numbers, let's call it H, these are what I call H. This is the H star, that's the truth, and that's the H, the field, if you want, of your model is trying to learn. So this is just a two-dimensional integral. And if you see something like G of H, you can use integration by part, or if you are a fancy mathematician, you call this a Stein lemma. And basically this guy is becoming G prime. So, okay, so now you have something even simpler. And now the trick, every time you are working with Gaussian integrals, Gaussian average, is to say, okay, let me expand this in the Hermite basis. Okay, the Hermite basis is the basis of polynomials where everybody is orthogonal. Right, so I expand these two functions in the Hermite basis. Here I have the Hermite coefficients. And now the good news is I can compute this very easily, because if k and k prime are different, all of this is 0, because the Hermite coefficients are orthogonals. And then what happens if I'm using the same and this? Well, the good news is that if you want to know what is the average of Hermite k of H and Hermite k of H prime, is just the correlation between H and H prime, which is what we call M to the power k. Right? And since M is small, the only thing that really matters is the first non-zero coefficient. So this is how it looks. This thing is just M at time t to the power L minus 1, where L is the first non-zero coefficient of the function you're trying to learn. Very easy. And that's it. Really, that's the ODE. And if you add 100 pages of math on this, you can write theorems, but that's really what it is. So it all depends, your teacher function. You expand it in the Hermite basis, and you look at which coefficient is the first non-zero one. Okay, this is called the information exponent. We give it a grandiose name. So if it is 1, that means your function has a linear part. You can solve this ODE, and it's easy to show that essentially with order D sample you are learning. If L is 2, which means you have only a quadratic part, then it's D log D. And if you have something which is more like cubic and so on and so forth, it's D to the L minus 1. So if you do this, your entirely ability to learn is governed by the first non-zero coefficient. So now what you can do is knock on the door of the computer science department and say, did you guys heard of this? And say, oh, sure. This is what is achieved with a slightly less good class of algorithms. They are called the correlational statistical correspondence, CSQ. We know they are not as good as SQ, and they do exactly what you are saying. You look like this. And what is the difference? Well, in SQ, you were asking, what is the average of any transformation on the data and the label. And here you are only allowed to ask average of transformation of the data, but you are linear in the label. Okay, so that looks like a coincidence until you see, haha, what we just did was computing expectation like this. That is why. Right, so this algorithm was part of the CSQ part, so it's maybe not so surprising. All right, so let me skip the next slide. It's not so interesting. And in some way, this is really disappointing. Okay, it's really disappointing because it's telling us that function like h to the power 3 minus 3h, which is the third Hermite, it has no Hermite 1, no Hermite 2, should be hard. And it's a bit weird. Why would the Hermite 3 function be hard to learn? And especially, it means that gradient descent is just not as good as all the things that we know in other places. So that will be a terrible and really unfortunate limitation of neural nets. But that's what was believed. Okay, and there are billions of papers that I'm just quoting here from really good people who worked on this. So those guys were looking to exception to the rule. They invented something called the staircase scenario. I would be happy to take about it offline. And there are tons of papers discussing these limitations. That these are necessary and nearly sufficient condition to learn. You cannot beat this, and that's what neural networks do. But now, if you remember, I did something a little bit weird. I said, you give me one sample, and I'm using it once, and then I throw it away. Who does this? Why would you do this? Why not, that's not, you can reuse data, okay? So they were discussing, well, can reuse data matter? And, they conjecture that it doesn't. Okay, so let's look at part 4, and the last one. What happens if I reuse data? If I do multipass algorithm, and we heard about it by Pier Francesco on day 1. All right, so turns out, if you start to reuse data, everything changes. And it's not at all what all those guys use. Of course, it's harder to analyze, but a physicist, you can do a simulation. So here, what is that I did? I took this function, the Hermite 3. It has an information exponent 3, because of course it doesn't have a Hermite 2 part and the linear part, right? And it's supposed to be something that you need d-squared data to learn. And that's what I did. I took a big batch of order d data, and I did gradient descent twice. And that's the overlap I get at the second step. That's the one at the first step, and I learn without problem. The single pass fail, the multipass learns perfectly. Epoch, exactly, epoch. Now it's an epoch because it's going through the same data. All right, so it's drastically different. Completely different. And of course, there are lines. Can you guess what the lines are? It's a theoretical prediction coming from? No, it's not replica, it's dynamic. DMFT. These are the equations of DMFT that were written by many people in the room. And of course, if we run them, we know what's going on. And it's the same with multi-directional thing. These are examples that are supposed to be hard to learn. And there are many papers saying how hard it is to learn this stuff. No, it's not. 2 steps. All right, so let me tell you what we could prove, and then I try to give you why it's true. Good news is that if you have a function without symmetry, with 2 iterations, you can learn a non-trivial guess of the directions. So it's just as good as the best thing that IMP could do by cheating, but here I'm not cheating, right? I'm just running a 2-step neural network, and my first layer is learning the direction. What about these easy directions? The one where you need something small. Well, it's hard to prove, but we believe, and we are working hard, that if your batch is large enough, of course your batch needs to be large enough, because we know that we need a large batch event for our IMP and TAP. Well, you can learn with log D iteration. And we also believe that if P is large enough, the coefficient should be the same as for IMP. But we are trying hard to see this is true, but we believe it. So suddenly we are really, really good, and of course the hard functions are hard. Okay? And how did we prove this? Well, we took the DMFT equation, we worked really, really hard, read everything written by physicists, read everything written by mathematicians, and then read even more recent work by the group of Montanari. Then we kind of proved this equation for discrete time, and then we look hard at them. We did not want to iterate this equation. Okay, so physicists are okay to iterate complex equations. Most people are not. They want to know the result without running this crazy equation. This is not so easy to iterate, right? For those people who have worked on this, I mean, for 2 steps it is easy actually, but So we wanted to be able to have a proof without running the equation, which we did. So it's great use of physics. Now, in the remaining part, I want to tell you why it works, which I think is why it's interesting. And in fact, there is one trick in which you don't even need the MFT, okay? Which is data repetition, right? So the trick is data repetition. It's not full batch thing. So first of all, in reality, most of the time, even if you have a data set, it's not the IID data set of everybody is different. You have a lot of repetition in many data sets. You have very similar points, or sometimes even the same point, right? These are CIFAR 100. You have really exact duplicates sometimes. It's even worse because these are exact duplicates in the training set and testing set. So, even if you don't want to repeat your data, you are going to see the same sample later. So there will be repetitions and gradient step over the same sample in your data. Second remark, many people are actually not using 1-step gradient descent, but 2-step gradient descent or 3-step gradient descent. There are many algorithms like this. They have names called extra gradient, look-ahead techniques. There is something called sharp minima aware, SAM. So it makes sense to say, fine, let's see the following thing. I'm going to throw away data, but instead of you give me data, I run it once, and I throw it away, you give me data, I'm doing 2 steps, and then I'm throwing it away. Right, so now I can forget about DMFT. I'm going back to my nice ODEs like the SAD and SOLA one, and it's much simpler to analyze. Okay, it's not as powerful as a full batch thing, but that will be enough to get something interesting. So you just do 2-step gradient on the same data. Okay, and that works. That is for my Hermite 3 function. If you just see data once, you don't learn anything. If you see data twice, you learn perfectly. And the same and the same. Okay, so just to tell you what we could prove. So essentially, the trivial function, well, I mean, we will learn, that's still amazing, by the way. We are learning them with ordered sample. All of them. If you don't have a symmetry, we learn them. We are just as good as AMP with this algorithm, which is just SGD with 2 steps. What about the easy one? The one that you need, a large batch. Okay, you need d log d steps. So you need d log d samples. So you lose a factor log d by not having, a full batch. Only physicists will care about log d. And not even them. I mean, Giorgio once told me that log of infinity is 6, right? So, that means it's a log of 6, even in the worst case. So, it's probably good. And we can even learn the hard ones with d to the r minus 1 with this algorithm. All right, so to finish now, so why is it true? Why is it that it's changing that much? And so it's kind of fitting to go back to the previous computation. So you remember when I started from this ODE before, right? And I had this expectation here. So what has changed? Well, what has changed is I don't have WT here. I have a W that I have already updated once, right? Because I'm doing 2 steps. So now my ODE is something like m of t dot is the expectation of all this, but I have done already 1 step of gradient here. So it's not WT, but it's WT minus gamma gradient. Okay, that's the only change. It's not a very deep change. But now you see that it's a much more complicated function that I have here, right? In terms of the fields and everything, well, I have W times H, that's what I call the field. Now I have the gradient here that depends on the truth. That is projected. I mean, this is much more complicated than that. So if I take this and I expand it, I'm tailoring it, you see that what I have is, instead of this thing, which was essentially linear in y, in the truth, is now linear in y times something super complicated with all possible power of y's. It's a much more complicated thing. And so if I try to use my Hermite game, now I'm going to lose because it's basically impossible. I mean, I have to really fine-tune things in order to have a 0 here. And even if I manage to fine-tune it to have a 0, it will depend on these coefficients. But these coefficients are different from neuron to neuron. So I can fool one neuron, but I cannot fool another neuron. So once you see data twice, they are basically constructions. And the thing that was linear is not linear. Okay? And that's where I want to end the talk. You go from computing averages that are y times a transform of your data. And once you reuse data, you have a function of your data and y. You are also transforming y. You are not linear in y, implicitly. And if I ring a bell, it means I have done a good job, because that was exactly the difference between the CSQ class of algorithm and the SQ class. Right? And just doing twice to the data allows gradient descent to be super efficient. All right, so I think it's time to conclude. All right, so that's it. So over-parameterized network can learn multi-index functions without cheating. Well, for some definition without cheating, I just need to reuse the data a bit, and then they can learn. And they do it efficiently. It's rather remarkable that, up to log factors, neural network can learn as good as the best thing that we have invented, knowing the problem and so on and so forth. So that's quite remarkable. And so, one of the things we can see is that there was perhaps too many works in theoretical machine learning, on dynamics when you see only one data, 1 point. That was essentially the dominating approach of mathematicians there, and for good reason. But the limitation of these things don't have to be the true limitation of gradient methods, right? And it's kind of cool. I think I'm very happy that using physics techniques, we could clarify the situation. And one of the things that was probably I could have illustrate more, but I think I tried to get the point, is that even though these are very simple models, these are simple functions, they illustrate the tight interplay between algorithm, right? You really have to think which algorithm you are using, architecture, right? Are you learning? Are you not learning? What is the size of P? We see that we need P to be large enough, and the complexity of the function to learn. And I think this is something which is very nice, and that's the kind of thing we can do with our techniques. Okay, I'm really done, and I thank everybody that participated to that. This is Lenka's and my team. We took this picture at Cargèse last year. And, it's not my team now. It was my team plus everybody who was ever in the team at some point in their life. Only few people missing. Jean maybe was not there, but he's here, so you can see him. And so thanks to those guys, and thank you for your attention.